Okay, so let's continue our discussion of the mean value theorem. I've just sort of summarized it on the board here. MVT for mean value theorem. It says if I have a function that's continuous on a closed interval and differentiable on an open interval, then there's going to be some x value c where the derivative at that point is equal to the slope of the secant line. So this is the algebraic formula for that. I can think of it geometrically as the slope of the tangent equals the slope of the secant. In applications, instantaneous rate of change equals average rate of change. And that's true for some value c in the interval from a to b. Why don't I just draw a picture to illustrate? Let's suppose I have some function that passes through the point a, f of a, and then we'll have the point b, f of b. So maybe my function looks something like this, passing through those points. Now I've just drawn a continuous function, okay, and it's differentiable, okay. Now it might not be two-way differentiable at the endpoints, but certainly even one-way differentiable at the endpoints if I just take one-sided limits. So this definitely satisfies my hypotheses. So what the theorem says is this: if I draw in the secant line, okay, you can see there's the slope of the secant line. There's got to be some place, at least one place. Now, the theorem doesn't say only one place. The theorem says at least one place in between A and B where the tangent line is parallel to the secant line. Now, what I'm going to do is just do a graphical inspection to see where that happens. So if I follow this curve along, somewhere right around here, it looks to me like that tangent line is going to be parallel. So there's a value of c. I'm going to call that c1 because that's the first one I found. Looks like as I come up, now we're going up, so that's definitely not parallel, but then we turn to come back down. Somewhere in here, there's another point. We'll call that c2. Okay. Now, that's entirely possible. It would be possible that there's just one. What's not possible is that there's no place where the tangent line is parallel to the secant line. There's got to be at least one by the mean value theorem. What the mean value theorem doesn't tell us is where it is. It just tells us that it exists. And that feels kind of abstract. This is a really important theorem in calculus. It's going to be incredibly important when we prove the fundamental theorem of calculus, which is, as you might guess, rather important, okay? But this is a little bit abstract, okay? And it's important that we know this theorem, but there aren't a whole lot of scenarios where you come across where you need to know that a point exists but not find it. So a lot of the homework is going to be just a little bit contrived. They're going to give you a function that's continuous and differentiable. So let's say we've got f of x equals x squared. Let's say we're working on the interval from 0 to 2, okay? And the homework will just say, state that this satisfies the hypotheses of the mean value theorem. So check that the hypotheses, that's the if part, of the mean value theorem are satisfied. And then find all values c where the conclusion is satisfied. Okay. So, for the first part, I would say that is a continuous function. It is continuous everywhere. So, in particular, it's continuous on the closed interval from 0 to 2. That is a differentiable function. It's differentiable everywhere. So, in particular, it's differentiable on the open interval from 0 to 2. So, the hypotheses are satisfied. Now, what that tells me is that I know that f prime of x is 2x. That tells me there's some place where f prime of c is equal to the slope of the secant line connecting these endpoints. I think I'm just going to draw a picture for that. Here's 0, 0. This would be 2, 4. the slope of that secant line, rise over run, would just be 4 over 2, which is 2. So there's got to be some point in this interval between 0 and 2 where the derivative is 2. Okay, well f prime of c would just be 2c has to equal 2. So c would equal 1. Okay. So we knew there was going to be a solution to this equation because the mean value theorem applied, and then we just found what it is. That's not usually what the mean value theorem is good for. Usually it's good for knowing that a point with this property exists, kind of like so the toll booth collector can say, I know you were speeding at some time. I don't know when it was. I don't know if you were speeding at 3:30 or at 3:45 or most of the time that you were driving here, but I know you were speeding at some point even though I can't pinpoint the time. That's how it gets used most of the time, but we don't have a lot of scenarios that we can think of where we need to know that something exists without knowing what it is. So a lot of the homework is going to have this form. Okay, back in a bit.